In Kubernetes, the pods running your application are inherently ephemeral. When they crash, the system doesn't try to fix them, it automatically deletes them and rebuilds fresh copies from scratch. But this creates a fatal flaw for routing network traffic. When a pod is rebuilt, it receives a completely new IP address. If your application components are hard-coded to communicate using specific IPs, that connection breaks the moment a pod goes down. To solve this, we configure a Kubernetes service. This component acts as a stable networking layer that maintains a permanent address and ignores the changing IPs of the pods underneath it. Assuming you have a running Kubernetes cluster and an active deployment, we are going to configure a service to accomplish 3 specific goals: discovering active pods, balancing network load, and exposing traffic to the audience. Implementing a service replaces these hard-coded vulnerabilities with a networking layer that persists through every pod crash and restart. Step 1 is tracking pod identities. Let's start with a baseline architecture of a Kubernetes cluster, currently running a single deployment with multiple replica pods. On the left side of this split screen is our standard deployment YAML. Inside the pod template, we added a specific metadata tag, reading app payment. On the right, the service configuration uses that exact same text as its selector. By relying on this configuration, the service ignores pod IP addresses entirely. It strictly watches your cluster's network for any active pod broadcasting that exact app payment label. Keep an eye on your spelling here. A common configuration failure point is a single typo or capitalization mismatch between deployment labels and service selectors. If they don't match exactly, the connection will drop. In this flow diagram, the original pod fails and its IP address dies. However, the auto-healed replacement spins up with the exact same app-payment label. The service instantly detects this match and automatically reestablishes the routing connection, so traffic continues flowing without manual intervention. Decoupling a pod's network identity from its IP address ensures your infrastructure is protected against individual component failures. With reliable pod discovery, we must now handle the pressure of high-volume traffic hitting those replicas. If you point all internal application traffic at just a single pod, that component will quickly buckle under the load, causing immediate bottlenecks while your other replicas sit idle. Targeting the service's stable URL sends a large block of 30 incoming requests to a single routing node. This activates automatic load distribution, mathematically dividing the requests into continuous streams of 10 packets for each of the 3 pods to maximize efficiency. Automatic load balancing ensures that your cluster maximizes its resource utilization and prevents any single point of failure under heavy user demand. With the internal cluster mechanics working, the final challenge is safely allowing an external audience to access the application. We govern these outside access boundaries by defining a specific type in the service YAML. You have 3 primary options to choose from. First, cluster IP confines traffic internally for isolated microservices. Second, node port expands the boundary, opening worker node ports for corporate network access without the public internet. Third, load balancer routes external internet traffic through a cloud load balancer directly into your cluster for public-facing apps. Behind the scenes, the Kubernetes Cloud Control Manager automatically negotiates with your cloud provider to provision a public elastic IP for this routing. Keep a critical warning in mind if you are a developer building on a local environment. Configuring a load balancer type without actual cloud infrastructure to back it up will fail. If you apply load balancer mode while using local tools like Minikube, the service will look for a cloud provider that isn't there, leaving the deployment permanently stuck in a pending state. To avoid this hanging state during local testing, strictly limit your configurations to node port or cluster IP. Selecting the appropriate service mode establishes precise boundaries for your application, ensuring traffic only originates from your intended sources. Let's review the final architecture. You've built a system that tracks dynamic pods using exact label matches, balances network load across replicas, and exposes targeted endpoints. To test this architecture yourself, open your terminal, run the kubectl delete pod command to manually destroy a running pod, and watch how your system reacts. You will see the replica set deploy a fresh pod, and the service will automatically route traffic to the newly healed endpoint without dropping any of your active user connections. As we watch this continuous stream of data routing around failures, it sets up our next step. In the next tutorial, we will advance to using ingresses to handle complex, path-based URL routing scenarios. Configuring these services provides the networking foundation required for any environment intended to handle live users and unpredictable traffic.